A couple things from the worksheet. Electric fields are kind of weird. Just kind of want to give us some little more exposure. Okay, so number 2, I made you pick between these two equations. Specifically, I made you pick what charge you're going to use. Okay. Again, here's how I think about this. Okay, let's say this is the Van der Graaf generator. And this is creating an electric field. Okay. As you go away from the electric field, as you go away from the source, the charged object, what do you think happens to the strength of the electric field? It gets weaker, it gets stronger, stays the same. It's weaker. Is everybody okay? So if you struggle with number 2, pay attention. Okay. As you go away from the charged object, you get weak. The electric field gets weaker. Which of these two equations describes that relationship? So what that tells us is Q2 is the charge on the Van der Graaf generator, the source. It's the one creating the electric field. And the packaging peanut is Q1. So I gave you the force. So you're going to use the charge on the peanut, not the 150 or 250, whatever the charge on the Van der Graaf generator was, number 2. Okay. Questions 3 and 4 were highlighting your detective skills to figure out the direction of the electric field or the charge based upon the direction of the electric field. I think in number 3 it said the field is going towards the charged object, meaning it's inward, meaning the charged object is negatively charged. So context clues like that help figure that out. Number 5, so you had, in order to levitate something, you need something to counteract the force of gravity. Okay, so it's being repelled up. So this is negatively charged. Hey, beautiful. Thank you very much. Nice name. You got a name on? Is there a name in there?
Oh wait, yeah, my name's on it, but I can carry it.
Okay. Beautiful. Thank you. Okay, so in order to, this needs to be repelled. So this surface needs to be negative. That's what created a downward electric field, because this is into negative. Okay. To figure out the math on this, the sum of the forces in the y direction are equal to 0, and you have electric force minus force of gravity equals 0. So I'm jumping over this quickly. That's force of gravity. And then electric force using this equation is electric field times the charge. Do that. Number 6 was full on. So H was positive, right? Yep, positive, and S was negative. So this creates an outward directed field. Okay, and this had a bigger charge than S, so this was negative, so there's less electric field lines going into this. Okay, I'm going to hit the heart first, part C, and then I'll hit the lines. So at the heart, this is creating, so we're using this equation for both the electric field created by each one of those separately. Okay, you get a number. We drop the positive and negative sign on the charge always when doing the math. Then this is a positive, so this creates sunshine. At this point, at the heart, that sunshine is going outward, goes to the right at the heart. Okay. The negative creates inward directed field lines. At the heart, that's going also to the right. So that is why we added the two electric fields, because both are directed to the right. Okay. So your electric field lines go out of positive into negative. They're always perpendicular to the surface. Some of those just go out into space. Okay. To figure out the direction of the force, you have two different ways you can do that. So you have a positive charge here. Charged object, little test charge, little scout. You can say it is tangent to the electric field lines. Okay, so that's the direction of electric force. You could have also done it from the fact of here it's being repelled by H and being attracted to S. It's less attraction because it's further away. The resultant of the blue and red should be the green. Okay, I'll do it in another location just for kicks and giggles. Okay, there. The force on this should be tangent to the electric field lines. So it's being attracted. Nope, bad. Mixing my colors. It's being attracted to the negative. It's being repelled from the positive. It's not that strong because it's further away. The resultant of those two gives you that. Two different ways to do that problem. Okay. I'm going to suggest looking at tangent to the electric field lines because it's just easier. That's one of the beauties, the benefits of looking at the electric field. Okay. Yeah, Mega. You gave us the direction up and down to figure out the force. Yeah. If you hadn't given us a direction, how would we know what direction to take? Direction of what? The electric field? Yes. Okay, so you know it was, so what I gave you was the charge on this. Okay. In order to levitate it, I need this to be repelled from this. So this has to be negative. And that is why the field is going down. Cool with that? Good question. Okay, so hopefully that helped put you on a little firmer foundation with electric fields. Got a couple more questions to wrap up our electric field lesson. Give that one a shot. Tell your neighbor. Correct answer is B. Electric field lines go out of positive into negative. Okay, so you might have heard of a capacitor before. It's an electrical component. At the very basic arrangement of a capacitor, you have two charged plates that are oppositely charged. There's a gap in the middle. And what this does is creates an electric field that's relatively uniform, constant throughout that. Okay. The reason why we like this in introductory physics is because it creates a constant electric field and you don't have to do calculus. Okay. Tell your neighbor. Correct answer is A. Okay, you could do this two different ways. I'm going to encourage you to do the second way, but I'll tell you the first way. So we know electric field lines come out of positive and go into negative. So this is positively charged, positive attracts negative, up, negative repels negative, up. Add those two together to figure out the force. Okay, that's the first way. The second way is incorporate or capitalize on the electric field lines. Because it's a negatively charged object, it's going to be forced in the opposite direction that the electric field lines are going. Good with that? Next question. Tell your neighbor. Everybody goes C. Kind of heard it all around. Okay. If it's positively charged, you know it's going to be forced in the same direction as electric field. So this is why we give electric field direction. We can figure out the force on positive or negative things based upon that. Okay. Last question. Share your answer. Correct answer is B. Experiences acceleration Unbalanced force. Wow, I'm sure that sounded good in the microphone. Excuse me. Red spike. Yeah, unbalanced force experiences acceleration. Good with that? Okay. Okay. So here's how you're going to do this. Oh, yeah. So long as your hand is in physical contact with the Van de Graaff generator, you will not feel any pain. Okay? Yeah, it's just people say this feels weird. That is, you'll see people go, and the adjective they use, wow, that is weird. Like that's what. Okay, so you're gonna hang on to this metal pole. So long as you keep your hand in contact with this, electrons can transfer. Where you start to feel discomfort is if you make electrons jump to you. That's where things are going to get slightly uncomfortable. Okay, so as long as you're in contact, you're fine. Jewelry, you're fine. That's in contact with your skin. Okay, does that make sense? You're good. There's no. Okay, so after I turn this off, what you're going to do is take this metal rod and you're going to touch it to the metal frame on the Van de Graaff generator, the blue thing, and you're good to go. And you step off, and you won't feel a thing but the weird experience. So, come on up. Yeah, Josie.
So you said what?
Step. Put on. Yep.
Oh God, I regret this.
You won't. Go like that. Stick your head. Shake your head. Shake your head. Okay, look at yourself. You see it?
Oh my God! Can I pull my hand away?
Yeah. You can. Now touch the metal. Did it hurt?
No, it just scared me.
Yeah, it's just weird.
I saw the
All right, so the the question. Okay, I have several questions, but the first one being the most obvious is like, why did her hair stand up? Okay, I'll give you a hint. What happened when you charged this thing? What happened when you charged this? What happened when you charged this? They spread apart. Why do they spread apart? They're repelling each other. As you touch the ball of it, the Van de Graaff generator, and it's running, you're being filled with electrons. Okay? And those electrons don't like each other. And it's enough to like repel strands of your hair enough to lift them. So it's not being attracted to the ceiling. They're just electrons repelling from each other. Good with that? Next. Yeah, Brock.
All right, what am I doing here?
Just stand on the styrofoam.
All right.
And put that down by your foot. Just not on the ground. There you go. Okay, I want you to listen as he touches the blue base. Crazy, right? Okay, now, what do you think that was the sound of? Okay, those. So, do you think electrons like to be in the ball and the person touching it? No, they'd rather be in a better ratio. Okay, so what you heard were the step leaders of electrons trying to go out to a different, better environment. And then the pop That was a little bolt of lightning. Crazy. Cool with that. Next. Okay. Now we're gonna do something a little different with Oliver. Okay. So if you want to see this, come around, but don't get too close. What?
Move the phone a little closer and
Is that better? Okay. Okay, watch as he brings the rod in there. Yep. Okay, you're good. Okay, next. Okay, Carter, we're gonna do something fun with you. Hop on up. No rod. Put your hand on that.
Oh, rod.
Put your finger out. Watch the tip of his finger. See it? Do you see it? What? Yep. Okay, so just hop down. It'll go through your foot. You'll be fine. See? Your feet are tough. So what that was electrons jumping off your fingers. So charge goes to the outer surface, but it actually collects at sharp points, edges. And so the electric field is strong enough that the electrons are able to jump out. Back in the day, they used to call that St. Elmo's fire. And ships at sea, the masts during a thunderstorm would have the tips of them would have those little purple flames coming off of them. They thought it was a good omen. Those were the ones who reported that were the lucky few that did not get struck by lightning. But does that make sense? So if you'd like to see lightning come out of your fingers, come on up. Yep. Cool. Yeah. All right, next.
I don't want to die, but I want to become a superhero.
You're not gonna die. Probably not gonna be a superhero. Yeah. All right, hop on down. Anybody else? Oh, this is so much fun. This is like probably your only time in your life you're gonna be able to do this.
without being in any immediate danger.
Well, yes. Ready?
Yeah.
Pretty cool. It doesn't hurt. Your feet are tough.
It's a little weird, especially as like your head part.
Next. Don't be scared.
I saw it on your.
Next. That's a good one. You guys? Yeah.
Your hair's a little upward. Whoa! It sounds like Steph's upward.
Next. Anybody else?
What if I grab it with two?
Same thing.
Same thing.
Yeah. What happens? You put your finger where? You'll get shocked. Yeah. Wait, a what? Yeah. We'll get the shock in here later this week. Come on up.
What if I took
Mr. Smiley, she shocked me.
and touched my clothing just exploded.
No.
Ooh, I saw that one.
I could see it. That was.
Can we do this tomorrow? I saw you first when I did that.
Anybody else?
I saw it.
Okay, we got one more demo. If someone could turn on the lights. Okay, try to figure out why this happened. Why did that happen? Tell your neighbor.
It only goes to the top first.
What if I grab the tiny